We are taking the CPU scheduling, which is a very important aspect of our operating system. So we'll look about the CPU scheduling concepts and various CPU scheduling algorithm, and why we need specific algorithm for different scenario. So the objective today is to introduce this CPU scheduling, and which is actually the basis of all multi-program operating system. We'll talk about various CPU scheduling algorithms as well, and we'll see how and where to use CPU scheduling algorithm. And the term which is the CPU scheduling and process scheduling and thread scheduling, these are often used interchangeably in various papers you see, books you see, and various internet material. So the basic concept is that we want the CPU to be busy always. We want that if some processes are waiting, these processes are waiting, we want them to assign it to CPU so that the CPU is always busy and the multi-programming can increase. Now the CPU is allocated the process by, first of all, there is a short-term scheduler. Then after that, once the short-term scheduler says, okay, this process has to be given, the dispatcher dispatches it from the ready queue, or it takes the control from the short-term scheduler and takes this process to the CPU. So if it is a uniprocessor system, there is no problem, one process may be running at a time. But when we talk about multi-programming, that is, we want multiple programs or multiple processes to run, then we want to see that in order or in what order the CPU maximizes its utilization. So we have two types of CPU, you can say, processes. One is input output bound, one is your computation bound. We have certain time which is given to it. See, I'll show you. There are CPU input output burst cycle. What it means, that when CPU burst is given, means the time which is given, what time the process takes in the CPU, and it is computation bound. So this is where the CPU burst is going on. Now the process is waiting, so this is the input output burst. Now again it is doing some task, or the CPU is operating on it, so it is CPU burst. Likewise, this goes on and on. So this is a cycle, and when the CPU burst end, there is a request to terminate the execution. Now what we see here in the histogram, we have frequency of the happening and also the millisecond, the burst duration. What happens at start, it is very high, then it becomes a kind of constant. We want that the CPU burst time should be in accordance with the maximum CPU utilization. So the input output bond typically has many short bursts like this, while the CPU, the input output bond, and CPU bond have large CPU burst. So in order to select the CPU shading algorithm, we have to know about this also. So what is a CPU scheduler? As we just said, that the process has to be brought into the memory first. This is done by long-term scheduler. Once they are in memory, they are to be put in the ready queue, and then now in this ready queue, one process has to be selected. This is done by short-term scheduler. Now once this has been done, this has to be given to CPU. This is done by the dispatcher. So these can be, the different form is, you can select the processes in terms of first in first out, in terms of process queue. So you need to have all the records of the PCBs, process control block, because you're dealing with processes now. There are certain types of preemptive scheduling, which is preemptive and non-preemptive scheduling. And see, in this non-preemptive or cooperative scheduling, what happens, the process is allowed to run to its completion. It is not being disturbed. It is never disturbed. It is allowed to complete, right? And there is no choice in terms of scheduling, because there is no preemption, but we'll see about that also. In terms of preemptive scheduling, the process, even if it is working, it may be temporarily suspended. It can be sent to a waiting state. From the running state, it can be sent to a waiting state. But what problem can arise? See, if you have process here, P1, this is updating its data and you have just preempted it. So P1 comes out from the CPU. Now you put P2 inside. So now P2 has taken the place of P1. P2 is on the CPU. Now it is being executed, or it is under execution. Now this P2 is dealing, or it is wanting to process the data, or it is requesting, or it is seeing the data of P1, but P1 was not updated, P was not properly updated, so there will be inconsistency what P2 will be viewing, because P1 is not updated properly. We have a dispatcher is very important, because as we said, when once the ready queue is there, in this ready queue, which process has to be selected is devised by, or is formulated by the short-term scheduler. Now CPU, who is the authority, who is the component, who is the module, which is the module which takes this process to CPU? It is nothing but the dispatcher. So dispatcher is the module that gives control of the CPU to the process which is selected by the short-term scheduler. So what task it applies, or what are the process? First is the switching constant. This is P1, this is P2. P1 has to be taken out. That means P1, all the state, all the information has to be kept, and P2, all this information it has to be reinstated in the CPU. So we also ought to know, it may be possible P2 might have been reintroduced. So P2 might have worked along, it has been executed for certain point, so it has to be restarted again. So dispatcher has to be as fast as possible, because dispatcher is invoked for every process. As we said, long-term scheduler, it has low frequency, short-term scheduler has very high frequency, but dispatcher, in spite of being high frequency, or along with being high frequency, it has to be very less in the latency. That is the dispatch latency, that is the time it takes for the dispatcher to stop one process and start another running. This is the dispatch latency. We want it to be as minimum as possible. Then we have a scheduling criteria. Scheduling criteria is based on various aspects, because different CPU scheduling algorithm, they have different properties, as we see just now, and the choice of particular algorithm may favor one class of a process over another. What are the criteria? First is CPU utilization. We want the CPU utilization to be as maximum as possible. Throughput, that is the number of processes which is completed, number of processes which are completed per unit time. This is the throughput of the criteria, or you can say the CPU utilization, this throughput of number of processes which are coming has to be as maximum as possible. Then we have turnaround time. That is, when you submit the process and the time it completes, the time in between is the turnaround time. That is the time of completion minus time of submission. This difference is nothing but the turnaround time. And what is the formula? Because now the turnaround time is basically the time it has got in the CPU, and the time it has wasted, or it not wasted, I must not use this word, it has passed in waiting in the ready queue, or say maybe some input output is going on. So CPU burst time plus waiting time is actually the turnaround time. How about the waiting time? Waiting time, as I just said, the sum of the period it spent waiting in the ready queue, all the time it was waiting in the ready queue. This is the waiting time. So the formula will be the turnaround time minus the CPU burst time. Then response time. Response time is, first you have submitted the request, the first point you get some response. I'm not talking about the total completion. I'm just saying the time the first response you receive, this is the response time. So what is our criteria when we are dealing with the CPU scheduling? First of all, we want to maximize the CPU utilization, we want to maximize the throughput, we want to minimize the turnaround time, waiting and response time. All three, these has to be minimized as much as possible. So scheduling algorithms, which process has to be selected from the ready queue, which has to be allocated to the CPU, they are various. First of all, first come first serve. There is no problem. The process which has come first will be allocated first, and the PCB of the process is linked onto the tail of the ready queue in the first come first serve. So whenever the CPU is free, it gets the process at the queue's head. Means here is the process, this is the head. So whenever CPU is free, it will get this. This is done, it will get this. This is done, it will get this. So it will be a sequential form, and the average waiting time, as you see here, is not minimum, because there will be a convoy effect. See, just assume that this is the scenario. These three are taking just 1, 2, say 3 burst time, and this is taking say 50 burst time. So the convoy is there whenever you are, whenever there is an army convoy going on, or a convoy of some big minister, then all the others people or all the resident have to wait. All the bikers or the the people who are on the roads have to wait. Even if this guy only wants to cross the road, he has to wait for all the time till the convoy passes. This is the convoy effect. When process wait for a big one to get off, this one to get off. So this is we can have a non-preemptive version, but we'll see the non-preemptive, because the process keeps the CPU until it releases it. This is not at all advisable for time sharing system, because at that time you want every process to get some equal amount of time, but this is not possible here. So we'll take an example. These are the processes P1, P2, P3. It requires 24 unit time to complete. This required 3 and this required 3. Because P1 has come, it will be allotted first. It will complete till 24, then P2 will be allocated, and then it will complete for 3. Then P3 will come, it will be allocated sequentially. Now what is happening here is, this P1 is waiting 0 time, but P2 has to wait all along till the P1 complete. This is the convoy effect. Now P2 has to wait till this time, 24. So this is the waiting time. P1 is 0. P2 is 24. Now P3 has to wait for P1 to complete and P2 to complete. So 24 plus 3, that is 27, it has to wait. So 0 plus 24 plus 27 by 3, this is the average waiting time. This is 17. Now suppose the order is changed. Let us change the order. P2 has come first, P3 has come first, and P1 has come. The maximum CPU burst taking time, P1 has come last. P2 will only, because it has just come, and because it has come first, we'll put it in the first in first out. 0 waiting time for P3, 3 waiting time, and for P1 only 3 plus 3, that is P2 and P3 completion, 6 waiting time. So 0 plus 6 plus 3 by 3, this is 3. This is much better. But convoy effect, short process behind long process. Then we have shortest job first scheduling. Now this is quite not very implementable type of scheduling, because this says that if we have these processes, P1, now this is executing, then P2, P3, P4, we will try to find out which of them is having the shortest time to complete. How to find that? This is a difficulty. This is very difficult to know in advance that which of them is going to be completed first. How to anticipate? Right? And if at all the time are same, then we'll apply the first come first service. So this SJF can't be implemented at the level of short-term scheduling, because there is no way to know the length of the CPU burst. How to anticipate? How to find out that who is going to be completed first? But let us try to predict the length of the next CPU burst. There are various ways. So the SJF can be either preemptive or non-preemptive. As we said that for FIFO, first come first serve is non-preemptive. We established that. SJF can be preemptive, it can be non-preemptive. Preemptive and non-preemptive means, preemptive means if a process P1 is running and P2 or P3 comes and this has shorter time than P1 will be taken out. It will be taken out and P2 will be given chance, whichever is less. And this is just knowing that this is the shortest remaining time first, because if the time remaining for P1 is lesser than P2 and P3, P1 will be allowed to complete. Otherwise, P2 will be taken. In non-preemptive SJF, the current place or current process is allowed to finish its CPU burst, then only P2 and P3 will be catered. As we just saw, it is very ideal. So it has a minimum average waiting time for the set of processes. Let us take an example. First of all, this P1 has come. This arrival time is very important. The arrival time. It has arrived at 0 and burst time is 7. So when P1 has come, no one is there. So P1 will be allocated. This is non-preemptive, so it cannot be preemptive. It will go up till 7. After that, because till 7 all has come. See, this P4 has already arrived because it has come at 5. But the P1 has completed till 7, so all have arrived. Now for the next sequence, we will see whichever he is having the less time, or which will be doing or executing in lesser time. P3. So we'll take P3. It will take 1 time. This is done. Now again we'll see which one has to be taken. 4, 4. Which one is less, because both are same. So we'll go with the first come first serve. So we'll take P2, it will complete for 4. Now all this is complete, this is complete, all are complete, only P4 is remaining. P4 will be given the chance. So the average waiting time for P1 is 0, P3 is 7, and P2 is, no, not 7. See, P3 has got the execution or the CPU time at 7, but P3 has arrived just at 4. So 7 minus 4, 3 will be the time for P3. P1 is 0. Now how about this P2? P2 has come at 2 and it has got time at 8. So 8 minus 2, that is 6. So this is the time. How about P4? P4 has arrived at 5. Where it was being taken, P4 was taken at 12. So you have to subtract 12 and 7, right? So you get 12 and this subtraction, because 12 minus 5. So you get what? You get 7. You get 7. So these are all the time, because you have to subtract the arrival time also. So 0 plus 6 plus 3 plus 7 by 4 is 4. This is the average waiting time. Now let us come to the preemptive time. Now P1, because there is no one, so P1 will be given chance. It has completed till 2, but by the time P2 has arrived, now this is having a shorter time than this. What is the remaining? 7 minus 2. So the burst time is 5. Its time is 4. So which will be taken? 4. P2 will be given chance. It will go up to 2, but by the time it has gone for 2 unit of time, P3 has come and it has lesser time, because 4 minus 2 is 2 and this is 1. So 2 and 1, which is lower? 1. So P3 will be given chance. After that, what will happen? Now because P2 is having a lesser time than others, 4, 5, 2, which is having lesser 2. So P2 will be given chance. Then after that, because now this has a lesser time, 4 and 5, so this will be given chance 4. So you can say that P1 will be taken last because it has the largest time which is remaining. P1 will come here, it will be completed. And I just discussed how to find the waiting time, because we have to find out the waiting time with this is the average waiting time. This will be this, which is equal to 3. And we see this is better. SJF preemptive is better. How to determine the length of the next CPU burst? You can estimate it. There are various things, like this can be done using the length of previous CPU burst, like this was the previous CPU burst. You can use the exponential averaging like this, and you can guess the time. Okay, if it has taken this much time previously, what it is going to take in the next. This is how it can be implemented. Now we have priority scheduling also. We can have preemptive as well as non-preemptive priority scheduling. In the preemptive priority scheduling, the CPU is preempted if the priority of the newly arrived process is higher than the priority of the current one. But in non-preemptive priority scheduling, the new process is put at the head of the ready queue, right? Then we have other options also. This equal priority, if the equal priority are there, they are rescheduled in the first come first serve order. So how these priorities are defined? It can be internal based on time limits, memory requirements, and number of files. And externally means it can be some other, it can be what is the importance of process, what is the political factor of the situation of the computer. All these can be taken. But there is a problem. There is a problem of starvation. In priority, what happens? If these two processes are coming and they have higher priority, the processes with lower priority will never get a chance. So they will be starved. They will not get food to eat. They will be starved. So what is the best idea? Whenever some other processes are coming, just increase the priority of these two lower priority processes. Then this is the solution, which is called the aging. So this is technically, or you can say the increasing the priority or the number, that is some number, the priority of the processes that are waiting in the system for a long time, so they will never be starved. Then we have round robin scheduling. So this is specially designed for time sharing systems. This is just like first comes first serve, but it involves the preemption. So there is a time quantum involved. This time quantum is very important. The ready queue is treated as a circular queue. So this will be circular queue. First this will be taken for some time, then it will be kept back in the tail, then this will be taken, kept it back in the tail, and likewise. So the ready queue is treated as a circular queue, and CPU scheduler goes around this queue, ready queue, allocating the CPU to each process for some time interval. This is one time quantum, and this time quantum can be in anywhere between these. So the ready queue is kept as a FIFO queue of processes. Now what CPU scheduler does, it will select the first process from the ready queue, set a timer to interrupt after one time quantum, and then it will dispatch the process. So what can happen? It may happen that the process may have burst time which is less than this one time quantum, so it will release voluntarily. But if the process has CPU which is CPU burst which is longer than one quantum, then it will go off. It will cause an interrupt to the operating system. Then this process will be put in the back, that is tail of the ready queue, and other will be taken. If there are n process in the ready queue and the time quantum you have decided is q, then each process gets how much CPU time? That will be 1 by n. 1 by n of the CPU time in chunks of at most q time units at once. So no process waits more than n minus 1 into q times. This is time unit. So the RR performance, round robin performance, heavily depends on one thing, that is the size of the quantum you have taken. If you have taken time quantum as very large, it is simply equal to first in first out, because all will be completed before the time or quantum time will elapse. But if you have taken q as small, time quantum as small, there will be various switching. There will be context switch, and that will be high overhead. So we have to reduce this context switch time, so that in order to reduce this context switch time, we will take the quantum time as good as possible. So just take an example of round robin. The time quantum is 20. So what will happen? P1 has come, 53. P1 will be given chance. P1 has completed minus 20. After it will be preempted. So the time remaining is 33. Okay, now P2 will be given chance, 17 minus 20, negative, so it will be completed. Let me put a tick. Now again P3 will come. This is simply first come first serve for with the preemption, and preemption is one quantum. The quantum time is 20 unit time. Now P3 has come, 68 minus 20, 48. Now 24 minus 20, now 4. So all these are done. Again P1 will come, 33 minus 20, 13. It is already completed, so this will never come. 48 minus 20, 28. 4 minus 20, negative, so it is completed. Now next, all these are done. Now again P1 will come. These are all done. Sorry, till here. P1 will come, 13. It will complete, because 13 minus 20, negative, it has completed. 28 will come, 28 minus 20, 8 is left. Again P3 will come, 8 units. See, 8 units. So it has high average turnaround than SJF, but the response is better. So we want the time quantum should be such that the context switching is as less as possible. We'll see the scenario where you increase or decrease the quantum. See, if the process time is 10 and the quantum you have taken is 12, the context switch is 0. There will be no context switch. There will be no context switching in the processes. But the thing is that the time is this quantum is very huge. I'm just taking an example. But if you take it as a quantum as 6, context switch will be only 1. Taken an example. But if you take quantum as very small, the context switch is very high. This we cannot accept. So turnaround time also depends on the size of the quantum, as we just saw. These are the processes, these are coming, these are the times. And when we take one quantum, it will be like this. Say 4 quantum, it will be like this. So we want the average time or turnaround time to be as least as possible. So we'll go along with either 6 or 7 time quantum. This is the time quantum. So this we have talked about the scheduling algorithm, but this is not done. We will be taking, because this is not complete actually, we'll be taking the multi-level queue and multi-level queue feedback scheduling is also there till the time. Thank you so much. Take care of yourself.